All right, let's do it. So this is chapter 4, chemical equilibrium. So, chemical equilibrium. Now, it's a so we know that again it's about equilibrium. But now when the reaction takes place, how do we handle the delta G is the real question. So now we know that delta G is equal to 0 at equilibrium. So if of course if the delta G is negative, let's say, all right, negative, then the reaction happens spontaneously, right? Reaction happens spontaneously. Now, remember the composition adjusts itself to the lowest energy point. All right, so keep that in mind. So, and then reach the equilibrium eventually. So keep that in mind. Now, so we're going to talk about the mixture. Mixture, and then again, mixture meaning that it's a concentration of solution. So when we talk about concentration, we talk about activity. In the previous chapter, activity has something to do with concentration, but also something to do with the vapor pressure. So again, but also we also have talked about delta G, the single component delta G. It's sort of like a partial delta G is chemical potential. So chemical potential of a species A is equal to chemical potential of species A when it's pure plus RT, natural log of activity of A. So, but activity of A is a vapor pressure. So it's a partial pressure, but the real vapor pressure when it's a mixture, with respect to when the divided by the standard pressure 1 bar. So if it's 1 bar, whatever the pressure, let's say this is, I'll just come up with a number. So whatever the vapor pressure is, so let's say, I don't know, just let's say 2.12 bar or something for the vapor pressure above the solution of the mixture. But then bar and bar cancels out, so activity in this case turns into 2.12. Again, don't write these numbers, but just to demonstrate that this 1 bar, again, I'm going to rewrite it, it's 1 bar. So this 1 bar just means that, so that the units would cancel out. So keep that in mind, right? So, but an activity, so what is activity? Activity actually tells you activity of the component of the mixture. Mixture is the vapor pressure above the solution. Is the actual, right, vapor pressure above the solution. So keep that in mind, right? So now let's look at the relationship between the delta G and the equilibrium constant. So now we're going to look at, right? So now, right, after this we're going to look at the relationship between delta G and equilibrium constant. All right. So let me actually erase this. From the previous, study, all right. From the previous study, remember the dG. is equal to minus SDT plus VdP. That's the relationship between the delta with G and heat and expansion. But in reality, right? What I didn't tell you earlier was for solution. So, but in reality, right? So in reality, with a reaction, or you can or solution maybe solution, meaning that not an ideal gas, so to speak, then you can call dG is equal to still minus SDT plus VdP. That part is fine, but also, so these are the gas component, but also you have a chemical potential, which is again partial delta G. Chemical potential is a partial delta G. So dG, so you have the sum of all the chemical potentials, right? Associated with the species I, because you have many species, right? And then the changing in number of species, and then of course I goes from 1 through whatever the number, right? So this, remember, this is a sum of the chemical potential, right? Changing, right? Changing, n, right? For species. Alright, so keep that in mind. But if you add all them up, then that has contribution for the overall changing in the Gibbs energy. So keep that in mind. It comes from the heat factor, and it comes from the expansion factor, as well as the actual chemical change, right? Individual chemical potential change, other than these two factors. So keep that in mind. Now that's it. So now let's talk about this number. So let's say number of species, let's say, so number of species for species I is a number of species I at the initial number, plus if the reaction takes place, then the number changes, but so the number comes from the initial number plus the stoichiometry, right? Stoichiometry number times the what we call extent of reaction. I use the symbol, Greek letter symbol. So this one right here is the extent of reaction. Extent of reaction. So how much or how far the reaction went, right? So this E-looking thing. Right? So now, so if you write it this way, and if you substitute this into here, then you get dG. You get dG is equal to let's see. So minus SDT plus VdP plus, and then overall, so if you change, so you add the sum of the stoichiometry. So again, stoichiometry times the chemical potential, right? And then now times the change in the extent of reaction, right? So again, so this just converts the number of change in chemical potential to in terms of the extent of reaction and the stoichiometry, all right? So, but of course, for at constant temperature and then constant pressure, then these two terms can go into 0, all right? So then I'm going to erase this. So I'm going to just erase this part right here, all right? All right. Then this part right here, you can just write it as dG over and divided by the d extent of reaction, while T and P is held constant, is equal to, what's left of is this sum of the stoichiometry times the chemical potential. Again, how it gets here is not that important. Just take my word for it. Earlier, you had from here it was converted from sum of the chemical potential times D and I, right? And I goes through whatever the species, right, to the number of species, right? But it got converted, right? So because Ni is equal to n of 0 I species I plus stoichiometry times the extent of reaction, right? So but anyways, so so if you have this equation right here, all right, then so what does this equation tell us, right? So now, interestingly, right, at equilibrium, well, at equilibrium, G is at its minimum, right? It's at its minimum. So what it means is that dG over the extent of reaction while T and P is held constant minimum is equal to 0, right? So you can call all the sum of the species and stoichiometry times chemical potential of species, all right, is equal to 0. So keep that in mind when you look at this, all right. It's interesting because now this is chemical potential. It's a G, right? It's a single species G. It's like a partial G times stoichiometry, right? And you're adding all of these partial G, right, with stoichiometry, right? Is what really is equal to 0, because again that's dG over the extent of reaction. So again that's so keep that in mind. All right, this term right here is how much G is changing with respect to the extent, how far the reaction is really going, or how much reaction is taking place. All right, so keep that in mind. So then it's equal to 0. We call this equation 1 for the time being, right? And also, by the way, right, we already know that delta G is actually dG over the extent of reaction. While T and P is held constant, because that, again, that's the delta G, because this, again, changing in G with respect to the changing in the extent of reaction, how much the reaction is changing or how far the reaction is going, right? So if that's the case, then we can call this equation 1 and this, we can call this as, well, so then, well, combining this and this, right, will give you, right, 1 and 2, right, gives, well, we can call it delta G is equal to sum of all the chemical potential with the stoichiometry. That's what it is. Is equal to 1, all right, is equal to 1 through n. That's all it is. So, okay, that's simple, straightforward. Okay, that's good. So that's what the delta G really means, all right? Delta G is, you have the partial Gibbs energy, and then how much the reaction is taking place, but then, you have stoichiometry. So again, you have to add all the partial Gibbs energy with respect to the stoichiometry, right? That makes sense. And then depending on whether it's reactant or product, it has a different sign, but we're going to come back to that. Anyways, so just to cover bases, all right? So now, chemical potential, by the way, chemical potential of species I at equilibrium is equal to chemical potential when it's pure of species I, all right, plus, RT, natural log of, you can call it Pi over, P standard, all right? And of course, we had another equation, chemical potential, right, at equilibrium, is equal to chemical potential when it's when it's pure plus RT natural log. We can call that activity, all right? I at equilibrium, all right? So this again, remember, it's again, this part right here is the activity, right? So what does it mean? So then, so we call this equation, let's say 3. So substituting 3, all right, into 1. So now if you substitute this equation into this equation, what happens? All right? When I erase this one. So then, so you have sum, right? You have sum of the stoichiometry times chemical potential, right? When it's pure, right? And going from I through N, right, is equal to minus RT sum of stoichiometry natural log of A I at equilibrium, because you have equilibrium, we have activity, right? So if you continue, then it's going to be minus RT natural log. Oh, by the way, this is I through 1 through N. That part is fine, right? And then I is equal to 1 through N, right? And then this is the stoichiometry times natural log, but times natural log. Remember, the n times natural log of m is equal to natural log of m to the nth, right? So we can use natural log of ai at equilibrium to the stoichiometry, right? To the stoichiometry, all right? Or in this case, nu I, all right? So I mean, which is fine, all right? So this part through this part is is this part right here. Now, so then, well, what do we care? But remember, sum of the this part right here is the interesting part. The sum of natural log of, let's say, AI at equilibrium. This part isn't that important, but then to the VI, all right, or nu I, all right, is the same thing. It's, I mean, you're multiplying is is natural log of AI, and to the nu I, right? And then plus natural log of AI. I'm just not gonna write equilibrium, but this is actually at equilibrium. But I to the I plus 1, and then and then this one is the nu I plus 1, plus, and then so on, right? It continues, right? So you're adding, it's sum, so you're adding each term, right? But remember the natural log, right? Natural log of m plus natural log of n is equal to natural log of m times n, right? So you're actually, you can convert, there's a multiplication relationship. You're adding, but then in fact, you can actually multiply, right, into all these terms. So you can call this, right, is equal to minus RT. And of course, you're not taking calc 2, but there's a symbol for addition for symbols, series of addition is sigma. There's a series of multiplication is called pi. So I'm gonna go going from 1 through n, and then natural log, or in fact natural log of pi, and then activity of I at equilibrium to the VI. Okay, so that's fine. So again, this part right here is just the pi. Again, remember, sum sigma is for this addition, addition, all right, and then pi is used for multiplication, right, for series, right. Right, so keep that in mind, right. So basically you have natural log of a, but then you can just, now your AI times a2 times AI third 3 and so on. So just go into the series. So so what does it mean? All right. Well, what do we care about this? All right. So this is delta G. All right. All right, is equal to, right. So, and if it's delta G at the equilibrium, we just it's standard delta G. All right. Is equal to, and this part right here is what we call equilibrium constant, and this is what? we call equilibrium constant. All right, and you go, wait, but so K is equal to pi, all right, activity of I at equilibrium, and of course I goes from 1 through n, all right, and Bi, all right. So, well, okay, I mean, what does it mean? I mean, we call this K, by the way, right? We call this K, right? We call this part K. So, all right, so what does it mean? Well, let me write this down. So delta G, all right, is equal to minus RT natural log of K. Oh, this equation looks familiar, all right? So now what does it mean? This equation, all right, tells that delta G and equilibrium constant are related. Oh man, this is interesting because now delta G, and I said this before, delta U, relates to delta H and delta S. Delta U has something to do with heat and work, and delta S has something to do with heat. But delta S and delta H together is delta G. Delta G is actually related with K. Oh boy, everything is related, right? Very interesting. Now, so of course, when you look at it, you've seen this equation, you know they are related, but this is the theoretical basis of how they are related, okay? And of course, when you look at, this, pi activity of this, and you go, oh, still don't know, this looks too fancy, this looks just too complicated. So K, so again, for those lost souls, confused souls, no problem. All right, so here, you got N and you got I is equal to 1 through activity of I at equilibrium, and then I'm just going to call that in VI. All right, what does it mean? All right, so let's think about this. For the case of AA, all right, plus BB going into an equilibrium, so CC plus DD. All right, so what does it mean? All right, so, well, remember, so in this case, equilibrium constant, all right, is equal to, well, without going back to this equation, let's just look at, what you know, all right? Basically, equilibrium constant is equal to what? So let's just, what you know. Well, activity, right, of product over reactant. So, I mean, equilibrium. So what you learned in, previous, lower level chemistry courses, activity is the concentration, well, you guys learned it as D times, C to over, product over reactant, and then you have a stoichiometry, so AA to the DD to the CC, right? Of course, that was the intro chem, but in reality, these are the concentration. It's based on activity, right? Activity of, based on, but it's based on activity. So basically, I'm just gonna put D. I don't I'm gonna just do D. All right, D and A. I'm not writing it right. So let's see. So here. So but based on its activity of D, right, times activity of C, right, over activity of A, times activity of B, and of course you have stoichiometry, C, and then A, and then B. Because, for diluted, remember, diluted system, which means, when the solute is not that much, and then the solution, the solvent is, predominant, then, for diluted system, activity is almost the same as the concentration. Activity of species A is almost the same as concentration for diluted system, right? And that's why you could use this assumption for the diluted system, and most of the time the concentration is good enough, because again the temperature doesn't really affect. I mean, it does affect somewhat, and that's why the equilibrium constant is not completely accurate. But as far as the diluted system concerns, it's a good estimation. That's why people use this for the equilibrium constant. But in reality, you're supposed to use vapor pressure. Anyways, going back. So guess what? This is what you learned. So activity of D times activity of C, and then stoichiometry D to the D's and to the C's, and activity of species A to the eighth times activity of species B to the Bth. Well, guess what? This is the same as this, right? You're multiplying right? So these are the series for multiplication. So in this case, if you do it this way, then guess what? It's going to be activity of species case D to the dth, right, times activity of, and of course it's at equilibrium, and cth at equilibrium to the cth, all right, times activity, because they're all series, right? Activity of species A to the minus eighth, right, times activity of species B to the minus bth, right? So therefore, the minus goes to the denominator, so it ends up being this. So keep that in mind, right? So this is the activity, again, so this is the equilibrium constant, all right? So again, it's the equilibrium constant, right? Based on activity. So keep that in mind. So of course, that's the equilibrium constant at equilibrium. No, this is at equilibrium. So of course, that's the equilibrium constant. So again, it's activity at equilibrium. If it's not at equilibrium, then you use the reaction quotient Q. It's the same thing. So it's pi times activity of the activity of the species I at any given point before it reaches the equilibrium constant. So I is equal through 1 through n. So is equal to, and then what you already know is activity of species A and activity of species B in the denominator to the eighth to the bth, and activity of species D to the dth times activity of species C to the cth. Right? What's the difference? Well, it's not at equilibrium. So keep that in mind. These are at equilibrium. That's why it's an equilibrium constant. So at equilibrium. That's why these are at equilibrium constant. This is a reaction quotient. So keep that in mind. This is a reaction quotient. And when you compare the reaction quotient and the reaction quotient and equilibrium constant, again, which one is bigger, which one, if it's it's bigger, and then it shifts the reaction toward that direction, like a La Chartier principle. So that's how the for the reaction quotient is used. So keep that in mind, right? So that's probably good enough for the time being, and then we'll just go for the next section after this, right? Right. Of course, the reaction quotient. So let's head back to the reaction quotient. So Q has something to do with the they should be compared to the equilibrium constant. But let's see. But before we move on to that, let's talk about delta G of the reaction. Delta G of the reaction, right, itself is, so would the reaction happen or not? Well, really depends. But remember that delta G is equal to, so just in terms of like all overall reaction is all the species I through n, and then the stoichiometry times the chemical potential at the standard condition at species I, so at the standard condition plus the deviation from it, RT, and then sum of all the reactions of natural log of activity of I, so of all the species. But of course, this part right here turns into the actual pi. So this term turns into this term right here turns into delta G of the standard condition, plus this part right here turns into RT, natural log of pi activity of I. Right? And then remember, this part right here is the reaction quotient. So again, so delta G of the reaction is equal to, well, delta G of the standard condition. Again, remember, standard condition at standard condition means at 1 bar. So of course, reaction may not be taking place at 1 bar, standard condition, right? So the deviation from the standard condition is this RT natural log of Q, right? So of course, so what does it mean, right? So what does it mean? So going back to that, all right? So if the reaction quotient, all right, is, say more product is there, all right? Let's say you have, so let's say Q is equal to activity of, let's say, D. Let's say it's all in, the reaction is, it's 1-to-1 ratio. So 1-to-1-to-1-to-1 ratio. AD, AC over, A and AB. Let's say. Just, to the first, all right? So the sake of simplicity. And then if that's the case, then let's say you have lots and lots of product. So if this side is the dominant, so in this case, it's going to be greater than 1, right? Q is greater than 1, all right? So if the Q is greater than 1, but natural log of greater than 1 is what? Is it negative or positive? I don't know. What do you think? And that sign would affect the overall, again, the reactions delta G, because even if this is negative, let's say, even if this is negative, in this case it's going to be positive, but depending on what the Q is, although delta G at the standard condition may be favorable, but overall your reaction quotient would affect overall the reactions delta G. So keep that in mind. So what does it mean? So in this case, again, so let me just write down what I just said. Q affects, all right? Q affects, all right, overall spontaneity of the reaction, whatever the reaction is in this case, right? So then, once you have the total delta G from this part, and then you can compare delta G is reaction is greater than 0, then, or, delta G of the reaction is smaller than 0, or delta G of the reaction is equal to 0, that would affect whether the actual reaction takes place or not. So keep that in mind. All right. So, probably that's good enough, right, for the time being. Let's see. Activity. All right. So let me just move on. So again, going back to the activity. All right. So we have used activity based on the vapor pressure, right? Because I mean it's a good good way to do it. So activity of, I'm just going to call activity of species J is equal to, again, pressure of species J. I've been using I, so I'm just going to switch it up a little bit. Just call it J, all right? And then, the P of species J, at the standard, which basically means it's one bar anyways. So, I mean, whether it's J or not, it's still 1 bar, so probably doesn't matter. So again, so P naught, right? So P naught, or we can call it, P naught with this, it just means 1 bar. So keep that in mind. It's a standard condition. Also, an activity of J, we can call that based on molality. So you can just have molality of species J over, again, standard molality, which is, it's 1 mole per, kilogram, right? So basically it's 1 molal, right? So that, the units would cancel out. Book actually says, BJ over B standard. I think might even say J. So remember, the book says, right, book uses, all right, your book may use, use J, all right, instead, all right, not J, sorry, B, all right, BJ, all right, so keep that in mind. Anyways, so of course, another term that you can use for activity is activity of species J is also if you use mole fraction. Again, this is based on the vapor pressure, based on the molality, which again makes sense because any of these are the concentration terms, or what you call temperature dependent concentration term anyways, because pressure, if temperature changes, that vapor pressure of that mixture will change. So again, that's the real vapor pressure of the mixture, real concentration of the solution in molality, but temperature dependent concentration. Or again, another concentration term that you can use for temperature independent, right? Non-temperature dependent concentration would be mole fraction. But so if you use mole fraction, there is something called activity coefficient. So activity coefficient J times mole fraction of J. This is something called activity coefficient. And then of course this is a mole fraction. So activity can be obtained in many different ways. If you use mole fraction in the temperature independent concentration expression, but then you have to actually convert that mole fraction into a activity by using activity coefficient. Right? Activity coefficient is given to you as needed, or you may have to find out activity coefficient based on the known activity, and then if you have a mole fraction, then you can always find activity coefficient. So keep that in mind. So keep that in mind, right? So of course, one more important concept that you have seen in the past, at equilibrium, by the way, just a review, delta G of the reaction, right, is equal to 0, because overall reaction, whatever the condition is, so non-standard condition, delta G of the reaction, non-standard condition is 0. Right? So then delta G of the reaction is equal to originally delta G standard condition plus RT natural log of K. But because this is equal to 0, we can call that as so is equal to 0. So then you can call this, right, is delta G standard is equal to, right, RT, well let's take that is equal to, so minus RT natural log of K, right? So then again, that's the relationship between for equilibrium constant and delta G are now related, and that's the equation you've seen earlier. But of course, if you try to solve that for K is equal to, and you can call that e to the minus delta G over RT. Again, you take the the exponential on both sides, and then you end up getting this equation. So both of these are often used, but again, this relates the delta G standard condition. By the way, this is delta G standard condition is the again delta G and equilibrium constant are related. How cool is that? All right, so keep that in mind. So all right, so then so let's stop for the time being, and then we'll take a break. All right,